All right, welcome back, Titans. It's the final lesson of the week. Should be hopefully an easy one after the one we had yesterday. It's just kind of expanding on interpreting graphs. Before we get going, though, I had two more jokes that students sent me that I really liked because I like bad jokes. But the first one was, how did one trash can break up with the other trash can? She said, "I'm dumping you." That might hurt if you just broke up. I'm sorry. Another one was, why did the skeleton cross the road? To get to the body shop. He needs a body. All right. Thank you for sending those. Moving right along, we're going to interpret graphs of quadratics. Quadratics come into play quite a bit in real life scenarios. So we're going to go over 4 different scenarios and answer some questions about them. So the first one, it's kind of a long intro, but a dog owner is trying to build a rectangular dog enclosure for his dog. He has 100 feet of fencing to work with, and the equation that he can use to determine how to maximize this area is A of W equals negative 2W squared plus 100W, where A of W is representing the area in feet squared, and W is representing the width of the fence in feet. I will tell you right now that usually we have you set up these problems in class, and they are a beast of a problem. But all you have to do is interpret it, so you have the easy job, which is probably the more important job, is that you can actually understand how to read the graph. So we've got this dog enclosure. We know that there's certain widths that the dog enclosure can be, and then we have areas that we will get. So kind of a cool thing about quadratics is you'll notice that if the width is really small, the area is really small. But as our width gets bigger, the area gets bigger, bigger, and bigger, and bigger until we get to the maximum area, which is the ideal dog pen to build. But if we make the width too big, then our area starts to become smaller and smaller. Because if you think about a rectangle, if you have a rectangle with a lot of width, there's not a whole lot of length. And since your area is width times length, you're going to get a pretty small area. But if you maximize your area, you're going to have a dog pen that has a good amount of length, a good amount of width, and when you multiply those together, you're going to get the biggest area possible. But anyway, moving on to the actual problems. What is the maximum? So the maximum for this problem is 25, 1,250. And the important question is, what does this represent in the problem situation? Well, we know that x represents the width, right? Because we can read our graph, the x is width. And the y is representing our area in feet squared. So by looking at the maximum, we know that the max area the fence can be is, well, the maximum area we can get, the highest our area can be is 1,250 feet squared. The other part, though, is the 25. So this area occurs if the owner makes the width of his fence or enclosure 25 feet. So again, another way to say that is if he makes the width of his fence 25 feet, he will have a maximum area of 1,250, which is the biggest he can make his pen. What are the x-intercepts? What do they represent in the problem? Well, our x-intercepts are 0, 0, and 50, 0. And again, we know that x represents the width and y represents the area. So if the width is 0 feet, right, because that's one of the x-intercepts, is a width of 0 feet, or 50 feet, that's the other x-intercept, is 50. If the width is 0 feet or 50 feet, what will the area of his rectangle be? Well, the area would be 0 feet squared. That's not a very good dog pen. If you have 0 feet squared of area, your dog has nowhere to play. Can't even fit your dog in there. So that would be a really bad idea, right? Because if your width is 0, it means you have only length and your fence is basically smashed together. Same thing here, the biggest we can go is 50, because if you do 50 for your length, that means 50 for your width, the other width is 50, and you've already used all 100 feet of fence and you don't have any fence left for your length. So you're not going to have any area. Long story short though, if we want to maximize our area, we make our width bigger and bigger until we get to here, which was 25 feet. Going along with this, another point on the graph is the ordered pair 10, 800. So right there is 10, 800. Interpret this point. Okay, what does 10, 800 mean for this problem? Well, we know that 10 is our x, and x is our width in feet. We know that 800 is our y, and our y is area in feet squared. So we can interpret that if the width is 10 feet, yeah, that's a 10. If the width is 10 feet, the area will be how much? It'll be 800 feet squared. So essentially the graph shows us, depending on what the different widths are, we can find the area of the fence. So if we go here, right, maybe a width of 5, then we can see what the area would be. If we go to a width of 20 feet, we can see what the area would be. It gives us all of the possible options for the width and the area. Again, another point on the graph is 30, 1200. We know that 30 is our width. So if the width is 30 feet, right, we want to always make sure we put the units on there. If the width is 30 feet, the area of the dog enclosure, or dog pen, we'll call it, will be how much? Well, it'll be 1,200 feet squared. So again, any point on the graph just tells us that for that given width, what area would we be able to get for the dog pen? All right, last question to go with the dog enclosure, and that is, what is the domain of the problem situation? Okay, so we know the function, the graph will go forever left and right. So the domain of the function is all real numbers. But in the problem situation, what is the smallest width that this person could make their fence? Well, the smallest width you could do would be 0, right? You could decide to build a fence with no width. That would be kind of weird, but you could. But could you have negative? No, you couldn't. You can't have negative width. So the smallest width would be 0 feet. And then based on the fact that he has 100 feet of fencing, if he's going to make a rectangle, he'd have to have the two widths be the same size, right? And so if you cut that in half, the most that the width could be would be 50 feet. If you tried to go bigger than 50 feet for the width, you'd use more than 100 feet of fencing. So the possible widths for the rectangle are anywhere from 0 to 50 feet. That is the domain in the problem situation. Not just the function, but in the actual problem. Similarly, the range of the problem situation is going to be different than the range of the function, because the range of the function would be from here down to negative infinity. But in terms of the problem, we're looking at the area that the fence could be. Is it possible for you to have a negative area when you build an enclosure? No, that makes no sense at all. It's not possible. So in context of the problem, we will never go below 0. 0 is the lowest area we can have. So the area, or the domain, or sorry, the range in this problem, the possible areas, right? Because range is our y values. The possible areas are anywhere from 0 feet squared to the maximum. And what was our maximum? Well, our maximum area was 1,250 feet squared. So this would be our range for the problem situation. Okay, the next example is Mark, who got a model rocket over spring break, and he is going to fly his model rocket from the ground. And we're given this function, and this is one of those vertical motion models that we did in the last lesson. But that particular equation describes the height in feet as a function of time in seconds. So our y-axis is height in feet. Our x-axis is time in seconds. What is the vertex? Well, we just look on our graph, and the vertex is at 4.25, 289. So that's easy to find. But more importantly, what does it mean in this problem situation? And again, it just comes back to reading the graph. Our x-coordinate goes with our x-axis of time in seconds, and our y-coordinate, 289, goes with the y-axis, which is height in feet. So we know that in 4.25 seconds, the rocket reaches its max height. All right, we know it's the maximum height because it's the highest the graph goes, so it's the highest the rocket will go. So in 4.25 seconds, the rocket reaches its max height of 289 feet. Ran out of room there, but 289 feet. Next question, how long does the rocket stay in the air? Well, if we go to the time, the rocket started on the ground at the time of 0. It flew up in the air, it reached its maximum, and then it hit the ground right here. How long after the launch was that? Well, according to our graph, that x-intercept is 8.5, which means it took 8.5 seconds until it reached the ground, which means it was in the air for 8.5 seconds. One last question on this page. Another point on this graph. So we put the critical points, right? We put our two x-intercepts, we put our vertex. But another point on this graph is at 7,168. So if I go to 7 and then to right here, and again, there's an infinite number of points on this graph. This is just one of the points. But what does this point mean? What does 7,168 actually mean in this problem? Well, that's right. 7 is our time in seconds. 168 is our feet in the air that our rocket is at. So after 7 seconds, the rocket is at a height of, great handwriting, 168 feet. So the rocket went up, it reached its maximum height, and on its way down, once we get to the 7-second mark, it is now at a height of 168 feet above the ground, and it is on its way down, about to crash in another 1.5 seconds. All right, the domain and range, right? We're really hammering the domain and range, trying to help you understand the difference between the domain and range of a function and the domain and range of the problem situation. So again, domain of the function, if we just graph the equation, it goes forever. Domain would be all real numbers. But in context of this problem, my domain is my time, and I'm specifically looking at the time that the rocket is in flight. So the rocket left the ground at a time of 0 seconds, and it returned to the ground at a time of 8.5 seconds. That is when the rocket is actually in flight. That is the domain that we would look at for the flight of the rocket. Similarly with range, we're looking at the y values. So we're looking at the height in feet. If we were just doing the range of the graph, it would be every y value less than or equal to 289. But since we're doing it in terms of the context of the situation, we're looking at what are the possible heights that the rocket could be at. Well, does the rocket ever go below ground? No, it doesn't. It hits the ground and stops. So the lowest height the rocket reaches is 0 feet. But the max that it reached was still our vertex y-coordinate of 289. So we know that the possible heights that the rocket is at is anywhere from 0 to 289 feet. All right. Angelo, my man, is throwing his football. He's up on top of a roof 80 feet above the ground. I don't know why he's doing that, but anyway, sounds interesting. And he throws the football up in the air, and he's kind of standing on the edge of the roof, and then the ball goes and it hits the ground 80 feet below. We're given the function that represents this. I went ahead and graphed it. We got some of our key points. The first question, what is the maximum height the football reaches above the ground? Well, to find the maximum height, we go to the maximum. So we go to our maximum right here, which was 2,144. But of those, which one is the actual height of the football? Well, we know that our y-axis is our height. So that means our y-coordinate is representing the height. So the maximum height the football reaches is 144 feet above the ground. Now the y-intercept, we haven't looked at very many y-intercepts yet. The y-intercept of this graph was 0, 80. What does 0, 80 mean in this problem? Well, again, all we have to do is look at the labels. 0 is our time in seconds. 80 is our height in feet. So 0 seconds is when he released the football. When he releases the football, what does the 80 mean? It means the football was 80 feet above the ground. So at the beginning, actually I'm going to write that different. We can write this a number of ways, but I'm going to say he threw the football from a starting height or initial height of 80 feet above the ground. Side note, if we're being honest, if he threw the ball from 80 feet above the ground and he probably released it 5 feet above the rooftop's really probably only 75 feet, and then you add in the 5 feet that he was above the roof, that's why it went from 80 feet. But anyway, just details. All right, a little bit of a different question. How long will it take for the ball to be at the same height as the rooftop as it falls from the ground? And we're going to go back to the 80 feet again, just because that's what we started with. But I know that to get to the maximum height, how long did it take from the time he threw it until the time it reached the maximum height? Well, he threw it at 0 seconds, and it reached the maximum height at 2 seconds. So we know that the ball had been in the air for 2 seconds when it got to the max height. But the question is, how long will it take for the ball to be at the same height as the rooftop? So here's the rooftop. And we know that he threw the ball up, and now it's going to come back down. And I want to know, how long will it take to get to there? Well, we know that parabolas are symmetric. So if it took 2 seconds to get to the max, how long will it take to get back to the same height it started from? Right? 2 additional seconds. So if it takes 2 seconds to get there, 2 more seconds to come down, that is a total of 4 seconds. Right? 2 seconds to get here, 2 more seconds to get back to the initial height. You could also just look at the graph to see when it's at a height of 80 feet. That is a time of 4 seconds. We're actually going to look at that more on Monday next week. Finally, the domain and range of the problem situation. Domain is all of the x values that make sense. For time, we're not going to go back in time, so we're going to look at the time where he released it from, which was at 0 seconds. And then I kind of covered this up, but this point right here is 5-0, which means the football hit the ground after 5 seconds. So the flight of the football went from a time of 0 seconds to a time of 5 seconds. For the range, we're going to look at how high the football went, right? The height of the football. And in context of the problem, the lowest the football is going to go is the ground, right? It started 80 feet above the ground. It's going to end on the ground. So the lowest it went was 0 feet. But what was the highest the football went? Well, the highest that it went was the maximum, which was 144 feet. So in context of the problem, the range is from 0 feet to 144 feet. If we were doing the range of just the graph, ignoring the context, then the range would have been everything less than or equal to 144. All right, I threw one more graph on here. I like this one because it's dealing with money. Specifically, if you were running a company and you were trying to find the ideal selling price for an item, right? If you sell the item for too little money, you're going to lose money. You're going to lose profits because you pay money to get the object and then you just give it away. You're losing money. But if you sell the item for way too much money, this parabola does go down. Actually, we would get into the negatives on this one because we'd have negative profit, which means we're losing money. But the x-intercepts, let me actually go back to this. What are some key things we can interpret? Well, the x-intercepts are 10, 0, and 60, 0. My x is representing the selling price of the item, so how much we're going to sell it for as a company. And then the y-axis is representing our projected profit. How much money are we actually going to make as a company? Not how much are we going to sell it for, but once we take away the cost of doing business, how much money do we actually get to keep? What is our net profit? So if I look at 10, 0, the 10 is the selling price. If we sell this product for $10, what will our profit be? Not too good. $0. I mean, at least we're breaking even. We're not losing money as a company, but we broke even. Well, what happens if we sell the product for $60, right? So we go try to sell it for $60. How much profit are we going to make? Well, we're not going to make any profit there either. So this one, we're probably going to sell a lot. We're just not going to make any money though, because we're not getting much money for it. And this one, we might sell a couple, but it's so expensive that we're not going to sell as many. So we're going to end up not making a profit. So if I'm this company and I want to maximize my profit, I want to get as much profit as possible so I can go on a nice vacation and pay my employees and do all that fun stuff. How much money should we sell this product for? How are we going to maximize our profit? Well, you guessed it. We go to the maximum. And the maximum is right here. So in order to maximize our profit or our income from this item, we should sell it for $35. Anyway, hope this is making sense, interpreting graphs. I think this stuff is very applicable because there's lots of graphs that you'll read on a daily basis or when you're watching the news or researching different cars or products or various things. And being able to read a graph is really important, whether it's a quadratic, whether it's a linear, whether it's a piecewise. It doesn't matter what type of function it is. We want to be able to read the graph. And it always comes back to read the labels. See what your x-axis is, see what your y-axis is, and then being able to read the points. There's some Khan Academy that goes with this. Hopefully that'll get you the practice you need to further help you understand this. And we are just rolling right along. Keep it going, Titans. Keep up the good work.